Hey guys, so I got a new toy for you today that we're going to talk about. We're going to connect it to the physics that we've been talking about. So no new physics today, with one very, very small exception. Otherwise, today is just focused on showing you what we did last night, but with a new situation. All right. So today I've got one of these little toys. All right. It is the kind that has the spring and a suction cup. You've seen these before. So we push it down. The suction cup holds for a little while, and eventually, to our uttermost glee and happiness, it pops up in the air. Whee! Right? So you've all done this before. You probably had one when you were a little kid, maybe got it at a fairground or a birthday party or something, and your mom subsequently threw it away, but they're still fun. So there we go. Pops up in the air. All right. So I have another video of me doing this with a meter stick so that we could see how high it goes. So let's take just a minute. We're going to flip over to that video, and then we'll come back and we'll do some math with it. So hopefully you saw that. I have written down our information here. If you look closely, starting when it launched up in the air, it started down at 0, the bottom of the toy. So when it gets to its maximum height, I actually looked at the lowest part of the toy so that we're being consistent. The lowest part of the toy was about 79 centimeters, which is 0.79 meters. If you need to go back and look at the video just to see that I'm not lying to you, go ahead. I also went ahead and measured the mass, which was about 50 grams, so 0.05 kilograms. All right. So with that information, we should be able to do what we did last night. Now remember, the first thing we did last night is we used kinematics. So I'm going to go ahead and build a table for kinematics where we've got x naught, x, v naught, v, a, and t. Now when we do this, we need to make sure that we choose good initial and final conditions. Our initial condition, our starting condition, is going to be the point where the toy is already moving upwards. So it's not going to be the moment when it's standing at rest, because when the spring launches it, it has some acceleration there. So we want to look at the instant it leaves the table, then the only force acting on it is gravity. The spring's not doing anything anymore. It's part of the object. It can't push on the ground. And so therefore, it's only that point when it leaves the table. Then we're going to look until it gets up to its maximum point. That's going to be our final condition. Okay, so this is our final, this is our initial. All right, now with the kinematics, hopefully you're getting a little bit more comfortable with this. We can go ahead and make x naught 0. We can make our final position 0.79. The initial velocity, that's what we're going to look for. The final velocity, think about it, when it gets up to that highest point, it's going to stop and then come right back down. So my final speed, so this was in meters, this is meters per second. The acceleration there is going to be, of course, gravity, because once it has left the table, the only acceleration is that of gravity, so 9.8 meters per second squared. From there, we do not have time, so we're going to ignore it. We're not going to look at it. And we should then be able to calculate the initial speed. So choose an equation. Don't choose one that has time. So hopefully you're going for this guy right here. Sorry, v squared equals v naught squared plus 2ax minus x naught. You should be able to put the numbers in and calculate that. So go ahead and do that right now. I'll do it quickly. You'll be able to see my work here, but at this point you should be somewhat comfortable with kinematics. All right, so that's what I got. 3.93 meters per second is the speed of this little toy as it left the surface of the table. All right, so let's go ahead. I'm going to erase that. We're going to now look at conservation of energy. All right, so here we go. So this is essentially our conservation of energy equation, right? For right now, we're going to look at the ball plus earth system. All right, so we're looking at the ball and earth together. Now, in this situation, notice that we have some initial kinetic energy, initial gravitational potential energy. We add whatever work gets done during the process, and then we've got final kinetic and final gravitational potential. So let's talk about those as the ball goes up. So as it leaves the table, again, we're using the same initial conditions. As it leaves the table, what type of energy does it have? Well, hopefully you recognize that it does have some kinetic energy because it's got some speed at that point. Now, gravitational potential, it doesn't have because it's basically on the surface. If we call the surface of our table 0, then it won't have any gravitational potential energy at that point. Remember, it will eventually have gravitational potential energy because we're talking about the ball and Earth system here, which is then how they are interacting. Okay? Work is going to be work done to any external forces. Now, in this situation, the only force is gravity. And if gravity is the only force, then gravity is internal. It's inside of our system, so we won't have any work either. So we can go ahead and take out that work. Now, in the end, when it gets up to its final position, it does not have any kinetic energy because it's at rest. So we can take that out, but it will have gravitational potential when it reaches that point. So now we can put our equations in. We know that kinetic energy is 1/2 mv squared. And we know that gravitational potential energy is mgh. So let's throw it in. So we'll have 1/2 times the mass, which is 0.05. Always put your mass in kilograms, not grams, just like your distances should be in meters. And then that initial velocity, that's what we're looking for, equals the mass, which is 0.05. Sorry, I didn't put the 0 on this one, doesn't matter. Times g, which is 9.8, times the height, which is that 0.79. Ran out a little bit of space there. It's all right. You get the idea, 0.79. And so now we can calculate. So when I calculate those, go ahead and work it on your own. I'll show you my work here as well. All right, so there you go. You'll notice that as we worked through, algebraically, we ended up getting the same launch speed as we did when we used kinematics, that 3.93 meters per second. Now, I do want you to notice that when I put in the acceleration of gravity, I just put 9.8. I noticed in class that a lot of people are still using negative 9.8. We only use negative 9.8 when we're using it for kinematics because in that case, it is the acceleration for the object, and we are defining up as positive, down as negative. Here with energy, it's not necessary to consider the up and down because we're just using height here from 0, and then this is just speed. And so the actual direction of the velocity does not matter when we're doing energy. All right, so we've done it through kinematics. We've done it through conservation of energy for the ball Earth system. We're going to do it one more time, this time just looking at the ball. All right, so for this last set, we're just going to be looking at the energy of the ball. So not the system of the ball on the Earth. That means that anything that the Earth does, including gravity, is considered as an outside force, and that will do work. So that's what we're going to see here in just a minute. So again, let's go through. Let's talk about this situation. The first thing we can do is recognizing that we're just talking about the ball. An object by itself never has gravitational potential energy. Remember, in order for there to be gravitational potential energy, we need to be looking at the connection between the ball and the Earth. And so therefore, we can take out this one and we can take out that one, because those will not happen. Gravity is an outside force. There is no gravitational potential energy. All right. The second thing we can do is, starting with the ball at the bottom, we do understand that there will be some initial kinetic energy as it's launching up. The final kinetic energy up at the top, just like in the previous one, that will be 0. So this one will be 0 as well. And so what we end up with, we do have work, right? Because gravity is going to be pulling down on that ball as it goes up. So we end up with, if I simplify this, that's 0, that's 0, that's 0. I end up with just kinetic energy plus work is equal to 0. Now you may say, well, how can I add two things together to get 0? Well, in this situation, what is gravity doing? If you remember when we talked about it last time with Chewbacca falling down, gravity was causing the object to gain energy as the object fell down. What's going to happen here? Well, as my object goes up, gravity's pulling in the opposite direction. And so gravity's going to cause it to lose energy. And so when we do put in our work here, we're going to put in a negative work. Okay, now if it's helpful for you, you can go ahead and change it to a negative right now, or you can just look at the force and distance later, recognize that the distance is positive, that it's moving, but the force is downward. So a negative and a positive end up giving you a negative later anyway. So it's totally up to you how you want to deal with that. Okay, so now the kinetic energy is going to be 1/2 mv squared. The work is going to be, remember the work is force times distance. Now the force is the force of gravity here. The force of gravity, remember that force of gravity is not the same as the acceleration of gravity. To get the force of gravity, you actually need to multiply the mass times g. So I'm going to do that first. My mass was 0.05 and g is 9.8. So the force of gravity is going to end up being 0.49. Now the units for force are newtons, but you don't have to worry about that if your mass was in kilograms and your g was in meters per second squared. So that's why it's so important that you always make sure that you use kilograms, meters, seconds, because then the units will be fine. We'll just be able to throw them into our equation. So let's go ahead and put these numbers in. So it's going to be 1/2 times the mass, which is 0.05, times the initial velocity squared, minus the force of gravity, which was 0.49, times d, which was that 0.79, and then hopefully that's going to be equal to 0 over on the other side. So multiply these two, the 0.49 times the 0.79. That should then give you this number. We'll add it over to the other side. Then we're going to divide by these two. So divide by the 0.05 and divide by the 1/2. And we should end up getting the same thing that we had before, is that we end up getting V0 squared equals 15.484. And when we square root it, we get the same speed as we did the first time. All right, so that's it for tonight. Same idea, trying to look at that idea of what are the types of energy that we start with? Are we adding energy or taking energy out? And then what are the types of energy that we are ending with? And by doing that, then we look at the conservation of energy, and we should be able to solve for some missing pieces, which is what we did here. All right, hopefully we'll continue to work on that in class, but this is kind of an introduction, follow-up introduction to that for you. So I'd like to wrap things up just by talking a little bit more about the energy of the toy. Right now, we talked about the fact that when the toy launched, that it gained some kinetic energy with which it launched off the ground. That kinetic energy could turn into the potential energy of the toy Earth system, right? We talked about all that. But the one thing that we didn't really mention is we didn't really talk about this spring. Where does that kinetic energy actually come from? Well, when I push down on the ball, I am exerting a force down on it over a certain distance. Remember, we said that work is force times distance. So when I push down on the ball, I'm actually doing work on it. I'm causing it to gain energy. The type of energy it's gaining right now is something called elastic potential. Elastic potential is energy that's stored in a spring or a stretchy cable because it's been stretched and it's trying to get back to where it was before, right? Which is exactly what happens to the spring, is that now the spring's trying to get back to its original position. So the spring toy together kind of store some energy in there. That energy that I used to press it down, there's some energy now stored there that when it finally, the suction cup comes off, that stored potential energy releases. Now, we're not going to put an equation with that for now. We'll do that later in the year. But I did want you to recognize that there is another type of kind of potential energy here, which is called an elastic potential energy. And that is being turned into kinetic when it releases and launches. All right, that's it.